All right, for lecture B, our main topic is going to be multivariable calculus, and one extra thing that I'm forgetting at the moment. I probably should, I'll just come to that quickly here, but I want to review the end of lecture A. For Friday's quiz, for example, you should know these facts. You should know the derivative of log base b of x is what you see over there, 1 over natural log of b times x, both at the bottom, which can also be split up like that, and written without a dot if you want, which is always putting next to each other. Again, when b is e, natural log of b is 1, so it's simplified to just 1 over x. Okay. Real quick Mathematica demo showing you how this is affected with changes in b. Let's see, I thought I had a demo here. Here we go. Yeah, here. So here's, I'm starting with b equal to e here. If b increases, that logarithm function actually doesn't grow as fast when b is large. You can see it looks flatter and flatter there. Its derivative is closer and closer to 0. It still does grow up to infinity, believe it or not, even though it gets really flat seemingly. It still ends up going off to infinity. If b is small, like less than e, 2 or 1.1 or something like that, then the graph of that logarithm grows seemingly very rapidly, at least compared to the other ones, and its derivative is higher. If b is between 0 and 1, it actually flips around. The logarithm, when b is between 0 and 1, actually is the blue graph that's decreasing. Its derivatives are negative, and its red graph is negative. Okay? So that's something kind of interesting, though it's not something you typically use. You should know the derivative of inverse tangent is this fact again, 1 over 1 plus x squared. I remind you once again, as you see at the top of the screen here, that inverse tangent is also called arctangent. So if you see a problem like this on the gateway or a quiz, find the derivative of arctangent of x. It's the same function. That's the inverse tangent of x. So its derivative is the same thing. That's also 1 over 1 plus x squared. Okay? You get the same thing. Because they are just different symbols, different names for the same function. Oh yeah, the other topic is for today is antiderivatives. So the physics department wants us to introduce 2 topics in chapter 3 that are not actually in the book, at least not explicitly. Antiderivatives are talked about a little bit, but not in a real explicit way. I'm going to be more explicit. These are also known as indefinite integrals. Here's the situation. Start with a question. Here's a function. Can you find another function whose derivative is this given function? That's the question you want to answer with antiderivatives. It's the opposite of differentiation. With derivatives, we got a function, we want to find its derivative. With antiderivatives, indefinite integrals, we start with a derivative in a sense and try to find the original function. We go backwards. That's actually, generally speaking, even more useful than taking derivatives. Anti-differentiation is, I mean, it's arguable, but in my opinion, it's more important as far as applications go than differentiation. Such a function is called an antiderivative. Every derivative fact is equivalent to a corresponding antiderivative fact. If the derivative of this function is this, then the antiderivative of that function is the original. Possibly adding a constant. You mind closing that door there? Possibly adding a constant. Because when you add a constant to a function, it just shifts the graph vertically. Vertical translation, it doesn't affect the slope of the graph. We allow for the addition of arbitrary constants since those don't affect the slopes. And we use something called indefinite integral notation for antiderivatives. So for example, the derivative of x squared is 2x. ddx of x squared is 2x. Therefore, the implication is the integral of 2x is x squared plus an arbitrary constant c. You see this funny symbol? That's the integral symbol. It looks kind of like an elongated S. And there's a good reason for that. Leibniz created this notation, not Newton. Leibniz thought of integrals as being sums in ways that we'll talk about. Not today. So there's a good reason for this notation. It's kind of like an S, a very pretty S. Integrals are kind of pretty to look at. Okay. I love symbols. I love pretty symbols. And my favorite Greek letter, it's called xi. If you make it carefully, it looks like this. Very pretty. If you make it fast, looks like that. That's a good one. It's so much fun to make, too. I call it squiggle sometimes. But the official name is xi. And you spell that X-I, xi. Symbols. Oh, it's just so pretty. You read this as the indefinite integral of 2x is x squared plus c, or the most general antiderivative of 2x is x squared plus c. If you differentiate any function in the form x squared plus c, you're going to get 2x. Now you might wonder, why is this dx there? I'm not explaining that today. Just because I say so. Okay? Because everybody else does. The derivative of e to the x is e to the x. Therefore, the most general antiderivative of e to the x is itself plus c. Some people say this is the most important fact in calculus. And therefore, this is also the most important fact in calculus because they are essentially the same fact. Fortunately, it's the easiest fact to remember. Derivative of e to the x is itself. Derivative of cosine of x is negative sine of x. Therefore, the most general antiderivative of negative sine of x is cosine of x plus c. Does that mean the most general antiderivative of sine of x without a minus sign there is negative cosine of x plus c? It does, but I'm not writing that down. Here's one where we're deriving the derivative with the product rule. Lefty right plus righty left. Left function, right function. You can, before I watched the 3 blue 1 brown video, I always said first function, second function. I'm serious. You know, I've been doing this kind of stuff for 30 years or so. 3 blue 1 brown convinced me to say left and right. Left function, right function, because it flows so nice. Lefty right plus righty left. Left is x. D right is the derivative of sine of x is cosine of x. Plus right, sine of x, d left, derivative of x is 1. So you can see there. If you were just looking at this thing and you were asked, find an antiderivative of that, you'd scratch your head and say, I don't know. I guess it would involve cosine and sine, but I don't know how. Actually, it would involve sine, but not cosine. You can still write this, though. This is still true, even if it's not obvious. If I just wrote this and said, what's the answer would not be obvious by any means. But because I can take the derivative of this and get this, that does mean this is true. Get what I'm saying? Because the derivative of this is this, the most general antiderivative of this, which I have right here, is the original function plus c. And the c doesn't matter because it doesn't affect the slopes of this function. Its derivative is still the same. The derivative of a constant is 0. When you differentiate this, the check it goes away. That pi in the quiz differentiates to 0. Okay? I put it there just to emphasize that. What I'm saying here is if I were to just gave you this problem and said, find the answer, you'd look at that and say, I have no idea. probably. But this is the answer because of that fact. We are going to have a few completion problems on the one due on Friday, where you have to find slightly tricky antiderivatives. You're told that any capital F prime is, oh, I don't know, 2x e to the x squared plus x squared e to the x squared, what am I doing? 2x e to the x squared plus x squared e to the x squared times another 2x. Maybe it's written like this. That's the derivative of some function. What's the function? Looks really complicated. How in the world? But if you're careful and think about the fact that this kind of looks like what you would get from the product rule, it maybe helps you guess the answer. A little bit of trial and error might be in order to guess that this thing might be the answer. Indeed it is. I guess I did the lefty-right thing in the opposite order. Let's switch it around. Left. Bring it backwards here. Left, d right, derivative of x squared is 2x, plus right, x squared, that's the right. D left, that's the derivative of e to the x squared by the chain rule. So I combined the product rule and chain rule, which made it a little extra tricky. The point is, though, some guessing can help you figure out the answer. So you got some problems like that. The point is to guess. Make educated guesses and modify your guesses based on these rules. Product rule, quotient rule, chain rule. You can do it. A little bit of multivariable calculus now. Let's put it in the context of a physical problem. What's the period and frequency of a harmonic oscillator, like a mass and a spring? So, if you got a mass attached to a spring, let's imagine we've got a wall over here, ice down here. The mass is inside a vacuum. Why am I doing ice in a vacuum? So that there's no friction. Here's a spring and a mass attached to it. Grab the mass, yank it away from its rest position, and let it go. It's going to oscillate back and forth. Its position will be a sinusoidal function if there's no friction. Now, of course, there's still going to be friction here. There's going to be friction in the spring itself with its molecules rubbing against each other, so to speak. So you can't completely get rid of friction, but you can try to minimize it and use a sinusoidal function model motion. Simple harmonic oscillators are quantities that can be modeled as a sinusoidal wave, one of those kinds of functions. You don't have to write that all out. We've written that before. And you can use either one. It doesn't matter if you use sine or cosine, it doesn't matter. Whatever is more convenient. Right? We saw that back in chapter 1. Right? Appropriate horizontal shifts, you can use either one. The graph is a wave, a sinusoidal wave, right? With constant amplitude, which is a pretty good model if the friction is negligible. Say the mass is m in kilograms, and say the spring constant k. Well, k is the spring constant. Its units technically are newtons per meter. Let's not get into details of what k represents exactly. Just think of it as the strength of the spring, so to speak. Large K maybe corresponds to a real stiff spring, like it's real thick. It would be a very strong restoring force, yanking it back to equilibrium and then past, and then it gets squashed and it wants to go back the other way toward equilibrium. And if K is small, that's not a very stiff spring, that's maybe more like a slinky. Still play with slinkies these days? You should Google or YouTube, on YouTube, do a search for old Slinky commercials. There's a little theme song that people my age remember. It's kind of a cute theme song. What is the period and frequency of the oscillation? These are probably worth writing down. The B turns out to equal square root of K over M. I'm not explaining why. Okay? Just trust me there. The derivation of that is based on differential equations. We probably will see why later this semester. The period, the time it takes to go through one complete cycle, we saw back in chapter 1 is 2 pi over b. And in terms of m and k, you can write that this way. 2 pi times m to the 1/2 times k to the negative 1. Essentially, I'm just flipping this fraction because the b is in the bottom. And the frequency is the reciprocal of the period. It's b over 2 pi. Right, that is 2 pi to the negative 1 power, or 1 over 2 pi if you prefer, m to the negative 1/2 times k to the positive 1/2. What we have here are two quantities that we might be interested in working with, and we'd like to know how they change as m and k change, as the mass gets bigger because you change the mass, or as k gets bigger because you change the spring. How do these functions change? We might like to differentiate with respect to either m or k. These are really functions of two independent variables, m and k. This is multivariable calculus. At its most basic level, it gets more complicated. But at the most basic level, these are two quantities, t and f, that depend on themselves, two quantities, m and k. You might want to graph such a function, and you might want to take its derivative. Now, on the next slide, I am going to show some derivatives, but in the interest of letting you write some more if you want, let's take the derivative of, say, the period with respect to k. You can write that as dt dk if you like, the derivative of t with respect to k. If you were using multivariable calculus partial derivative notation, however, you'd write the d's in a fancy way. Sort of a curvy d. Calc 1 version, multivariable calculus version, multi-version. I'm saying they're equal. Yeah, they both represent the derivative of t with respect to k. Treat the m as fixed. Treat the m as a constant. They mean the same thing. They're just different notation. Don't let it bother you that it's different notation. And you may see this in your science books again. Sometimes they may use a d, sometimes they might use a curvy d. Don't let it bother you. It's just kind of a reminder, hey, this quantity t depends on more than one variable. If I want to think of these things as being variable. And again, I say, whether something is a constant or a variable is all in your head. It's just a mode of thinking. I can think of either m or k, or both, as being variables if I want. When I do differentiate this with respect to k, I do pretend the m is constant. And by linearity, this constant, 2 pi m to the 1/2, just gets carried along for the ride. And I just differentiate the k part with the power rule. And then you just simplify a little bit. The 2's cancel. You can bring the negative sign out in front if you like. You can write it like this if you like. There's lots of different ways of writing it. By the way, in the quiz, x squared root of x can be differentiated with the product rule, but you can also just differentiate it with the power rule. It's a little quicker to do it with the power rule. Either way is okay. That's a negative quantity. M and K are positive. It's got to have positive masses and positive spring constants. So that's telling you the period, how long the oscillation takes, going back and forth, decreases as K increases. The stronger that spring, the faster the oscillation, the smaller the period. You can also differentiate T with respect to M. And again, you can write it either way. Treat the K like a constant, right? The constant here, 2 pi, K to the negative 1/2. Differentiate this with respect to M. Get a positive 1/2, M to the negative 1/2. That can be simplified to pi over square root of M times K, which is a positive quantity, a positive derivative. If you increase the mass, you increase the period, which means it's a slower motion. Got a big mass like a house attached to that spring, it's not going to move. Well, actually, if it's on ice, it will move. But as long as that wall is really, really strong. But it will move very slowly. This slide has just more of these partial derivatives here. I can also differentiate the frequency with respect to M. The frequency is just 1 over the period. F, I usually try to write it with cursive, is 1 over T. T is 1 over F. When the period is big, slow motion, the frequency is small, it's slow motion. On the other hand, when the period is small, that's fast motion, it's a high frequency. Last thing to show you today is just a quick graph. A couple graphs, actually. How do you graph a multivariable function? In 3D, whoa! You got an m-axis going to the right here, a k-axis going into the screen, and a third axis going upward, labeled period here and frequency there. As m and k change, as you change that mass and you change that spring, you get different periods given by the height of the graph and different frequencies given by the corresponding height of the graph. We'll think more about these graphs as well on Friday. See you then.